Migrating from a monolithic solution to an event-driven architecture can be a daunting task, but it's a journey that more and more organizations are embarking on to enable greater agility, scalability, and innovation. Today, I'll be sharing practical insights and techniques based on a real customer journey that you can apply to your own migrations. I'm Martin Kilbride. I work as an AWS consultancy based in the UK called D55. My typical day will be working with different clients and different architectures, specializing in cloud native and serverless technology. So the patterns and problems I'll be sharing are based on a real life migration project that I completed. The project was for an online gaming company where the starting architecture was a monolithic .NET framework application that was running on Windows servers. The backend was a large Microsoft SQL Server database. So when a new customer registers against the system, then automated checks need to be ran to confirm the customer's age. And these are actioned by calling a third-party API. Only if a positive result is returned are they allowed to add money to the account and then play. But if the result is uncertain or if there's a failure, then the account is locked and the customer is asked to contact support staff. So the code for this whole process is all within the registration endpoint of the application, making synchronous calls to kind of multiple internal classes, which ultimately made that HTTP call to the third party and then process that result. So the goal was to have this application broken into different domain-based services. So all the functionality for a specific business domain was situated in the same location, whether that was a simple service or maybe a set of services within a kind of bounded context. The coupling between these domains would ultimately be looser than the monolith. And as an example, a change to, say, age verification related functionality, such as the integration to that third-party service, would all be limited to that single self-contained service. So specifically, we implemented this new age verification service. The only communication with the rest of that whole business application was initially via events. But later on, we did add read APIs for other systems to be able to check if a user is verified on demand. It had its own database that stored verification results and audit history, and obviously had the integration with that third-party age verification service. So I'd like to walk through the introduction of this new service by talking through several patterns and how they were used to do the integration and to do the whole migration. Starting with the Strangler Fig pattern. So coined by Martin Fowler about 20 years ago, this pattern is named after the Strangler Fig, which seeds in a tree, and over years it actually kills the host tree and replaces it. So as a metaphor, this is stuck around to represent that process of gradually replacing an old system around the edges, with the new system around the edges of the old, letting it grow slowly over several years until that old system is made redundant. In this migration, we actually started with this registration age checking process, extracted that particular behavior out, but left the rest of the system as it was. And then once that feature had been extracted, and over time, that monolith was reduced to the point it became obsolete by us extracting more and more of these specific business features. The second pattern I'd like to cover is the event pattern we used. Obviously, as an event-driven architecture, it's quite key. So specifically, we use the event notification pattern. So an event notification is when a system sends event messages to notify other systems of a change in its domain. But the important part with this pattern is that the source system doesn't care about the response. It's simply just broadcasting that change and throwing it over the wall, so to speak. This is different to other event patterns, such as event sourcing, for example, which is also a type of change event that's being published. But the idea with event sourcing is that every change is a change of state that's being published, and the event log can be used to actually rebuild that system or the state of the system. So in this particular application, we fired a notification when a customer registered to the website, for example. Any systems that needed to perform asynchronous actions off the back of that could simply use that event, but that registration process didn't care either way. So our next pattern is called dark launching. This is a pattern to call a new feature, but without using its results to assess its impact. The idea is to keep using the legacy code, but run the new code side by side in such a way that the output is actually ignored, running in the dark, so to speak. In this scenario, the event notification is fired on registration, but the existing code continued to run. The new system used this event to run the age-related checks, calling the third-party service, storing the result in its own database, but the output event of that system is not actually emitted, or it wasn't actually emitted and wasn't used. In this configuration, it was running like that for several weeks, and reports were ran against the old database and the new database to check that they are in sync. And that new service was in such a way meant it could crash, it was deployed with downtime, none of which caused any kind of problem for the customer. It allowed all the logging, the error handling, performance to be checked and risking no issue for the customer or the system as a whole. Now, pattern number 4 that I'd like to cover is feature toggles, sometimes called feature flags or feature switches. Now, feature flags come in different flavors, but in this scenario, we're talking about the use as release flags, which are typically used within trunk-based development and continuous delivery. The idea is that new features can be added behind a simple Boolean check, a check that can be switched in config, and ideally remotely and without a release ultimately. That code can be released to production rapidly because them new changes are not actually being executed. And then that flag can be switched on in a staging environment for testing before it's actually enabled in production. And then after a certain bedding in period, that flag and that old code can be deleted safely. So in this project, we actually put a feature flag around the legacy code. So the event notification is firing in both scenarios, but the flag surrounded the code that did the age checks in the monolithic legacy way. So the flag was set such that when the flag was enabled, the legacy code wouldn't execute. So it was the opposite to enabling new code. So at the top here is the pseudocode for the original process, and the bottom just shows the addition of that flag. So when the new system replaced the old completely, then that switch allowed disabling of the old functionality and at the same time enabling of the new functionality if need be. And then after a period of time, that whole section of code and the feature flag could be deleted. Now, the important part here is to have a flag which could be activated remotely if possible, because then it can be checked across multiple systems, which if you've got a distributed event-driven system, then you potentially want to check that in multiple different systems and your old legacy application at the same time. And then you can switch, and at the exact same time, that change will propagate across the system. Now you can use third-party systems for this, such as Launch Darkly or ConfigCat, a cloud-based service such as AWS's parameter store, or even just some sort of simple internal HTTP service, ideally with caching of some sort. But ultimately, as long as you can switch without a release, possibly, you can do it with releases, but ideally you would like you want something that's quite rapid to switch. Now, the final pattern I'd like to show is the legacy mimic pattern. Now, this pattern is to fill a gap where the existing system has some kind of contract. and the new system has to continue to fulfill that contract. So for this particular project, the monolithic database is used in many areas of the code. And Boolean checks are ran to check if they are verified, and lots of other options, but in this specific use case, it was just the age verification that was the important part. So it's important that the new system also updates that same flag so that all of the old monolithic code can continue to check against that database. Now, one alternative option to this is to change the old system, the monolithic system, to make HTTP calls to the new service to check if they're verified. But that might not even be possible. In fact, in some scenarios, it might be making that check in a stored procedure or in a database trigger. So making a HTTP call is not really an option. So to maintain the contract and reduce the amount of work required, then a legacy mimic was used here by persisting the result in the database still. But to avoid that new service from having to touch the legacy database, especially if you've got many of these services doing this, then we actually have an event being emitted from the age verification service. And then, so like such as age verification failed or succeeded, for example, and then have a legacy mimic service, which is listening for that event. And its only job is to update the legacy database. And that service was eventually decommissioned. So this is the final solution for the service. So a customer registers against a monolithic system, as they always have done. And due to that feature toggle, the legacy code didn't run. Now the event was fired to the event bus as an event notification saying that they've registered. And the event bus distributed that event to the new age verification service. Now the age verification service would then call the third-party API that we're using for verification. And then based on the result would run some kind of business logic and then store the result in its own database. Then an event notification was fired from this service back to the event bus with the result of the verification for a customer. And that was then fired from the event bus. It was routed onto the legacy mimic or our monolith contract service. That then was persisted into the legacy database. And that allowed the monolithic legacy system to continue doing age verification checks against that database. When this was in place, we actually then made a subsequent change to do age verification when a customer's address was changed, for example. And a small change was made so that the administration tool would also publish the same kind of event notification. In this case, it's a change customer address type event, but that was routed in the event bus to the age verification service such that the age verification service would run the same functionality as when a user registered, and then the rest of the system would stay as is. So in this new scenario, now all of it being in one service means that the third party that's being used for verification could be changed. The business rules around what happens based on the result can be changed. There was a change to add a circuit breaker, for example, so that if that third-party service isn't working, it could fall back to some other kind of business logic rather than relying on that third-party service. The database that service was using was actually a completely different technology. In this case, instead of Microsoft SQL Server, we could run using, say, a NoSQL database or a MySQL database or another technology that's more suited to the specific use case. The service itself could be written in a completely different language as the monolith and also to the other services, especially if you're running something that's, say, a container or serverless where there is no dependence between them. And even different development teams can work on different services very self-contained. But what about problems with this? What kind of issues did we come across?
So the first is probably latency. So monoliths might generally be a problem to work with. They're very hard for developers to work with. You tend to get a lot of behavior there that will cause bugs and so on. But by processing synchronously and all within the same process, they can generally be quite quick. By introducing asynchronous processing, along with the different layers such as event buses and multiple different microservices, it can take longer to get the same result, even if that new architecture is more resilient, more scalable, and doesn't have the same kind of flaws that the old system had. So to walk through an example, when a customer registers, then an event is fired to the event bus. The event bus then routes that to this verification microservice, which then hits the third-party API and runs its domain logic. And so let's say in this case, the customer failed the verification. So a verification failure result is fired back to the event bus. Now, at this point, the customer maybe tries to go and deposit some funds to their account so they can play a game. Now, the monolith will go to the database and read the verification result. But there's no failure in the database because in this scenario, at this point in time, we've not yet persisted the result from the verification. So in the background, the event bus is now routing the failure result from earlier to our legacy mimic service, and that's being persisted, but it's too late. So the resolution for this is very dependent on the use case. Obviously, I can only talk for this specific use case. But for this particular service, the trick is simply down to how it's stored in that legacy database. So if it's defaulted to false when a user registers, then unless you get a pass, then they're unable to perform any actions. So it's the safer option, but it can be quite jarring for the customer as it may pop up saying they're not verified when they go to add funds and they don't know why they're not verified. Now, if it defaults to true, then the customer has a great experience, but somebody who isn't verified could perform actions when they shouldn't, especially if that age verification service crashes, for example. So this could be very serious, such as allowing underage customers. Now, if it defaults to an empty or a null value, then it's probably a good middle ground. And we found this in multiple different services, not just age verification. So as the monolith can show a specific message in the case of an empty result that explains that verification is in progress. Now, the second problem, which is somewhat related to latency in some cases, is race conditions. The problem with asynchronous processing is that events can fire out of order, be delayed, overlap with each other, and so on. So let's say a customer registers, an event notification is fired, and the event bus will route this to two services in this example. So the first goes to a age verification service, which is going to run the same verification checks as we've discussed previously. The other service that's going to get the event is, say, a customer special offer service. So new customers will get assigned some kind of special offer. Now, this service at this point is just going to register the customer in its local databases. Because it's microservices, it's going to not have access to the monolithic database full of the customer information. So we're going to register this customer in our database so that later on we can assign a special offer to them. Now, the age verification service gets a result back. Say they passed verification, that gets fired to the event bus, which routes it to the customer special offer service. It can now go, okay, we've got a verified user. Now we can read that user from the database and we can perform some sort of business logic and assign them a special offer. Now, if the registration event that comes in doesn't get sent to the customer special offer service immediately, then in this scenario, we'll go to the database, we'll read the customer from the database, they won't be in the database, and so that service is unable to perform its action. Now, it might be that the event now does arrive, but it's too late. Now, when using events that aren't orchestrated, like the latency issue, the resolution does depend on the use case. So it depends. There's a few different areas to consider in this. So the first is just the type of event bus. It's very possible that if using a first in, first out type guaranteed ordering system, then that might reduce the problem. But that can sacrifice other aspects of the system, such as scalability, and increases the impact of having that kind of poison pill message, which is blocking a queue, for example. If it's a pub subsystem, then obviously that error could, it might hit the service and then the kind of event is lost. Whereas a queue, it might sit there for a long time. The other is just understanding the error handling and retry system of that event bus. So if the event bus does a fire and forget to the service, which is similar to a pub sub type system, then the event bus won't know that it's failed to be processed. But if it needs deleting after being processed, so it's a queue example, it's pulling the message from the queue, processes it, and then deletes it from the queue, then the resulting service can just simply ensure it doesn't delete the event in case of a failure. Based on the timeouts and the other configuration, that event will get fired again in, say, 30 seconds, and then it may get handled successfully. If it's a fire and forget type system, then the system might have to queue it in some other way, such as a dead letter queue. It might have to hold on to it until that registration event arrives. Or it might just be simply accepted from the business that in some cases, the offer just doesn't get assigned. In general, it's always better to check if it's fine to do nothing before doing something quite strange to handle them exceptional cases. You can put a lot of effort into handling exceptional cases when it's such a rare event that it's not worth doing any special changes for it, and just allowing, in that scenario, maybe the customer rings up and customer service will deal with it manually. Now, another option is just to not store that customer information locally. So change it to do a read API call to a customer data service, for example. Now, this increases that direct coupling between services, and it potentially reduces scalability. But it can also make that specific service, so the offer service in this example, might make that a lot simpler to actually implement, because you don't need to store any data in it, and stops synchronization problems and so on. So, but the options could also be combined. So in the case where it hits the database, the customer isn't in the database, so it then does a read to the customer data service and persists the details in its database. But you just need to be really careful with them kind of special cases, because it's a exceptional case. You need to make sure it can be tested, and ideally with automation, so in every release that specific use case is being tested. Now, the third problem I'd like to talk about is around idempotency. Now, idempotency refers to the property of an operation where repeating it with the same input has no additional effect beyond that initial operation. So in the example of this offer service, let's say an event is received that causes the service to assign them a special offer. If that event is fired again, whether that's because of an error somewhere, or because maybe the event bus doesn't guarantee at least once delivery, maybe it will send that event twice in some scenarios, that second message could hit the service, and the service will go and assign them a second offer, and maybe them offers stack, and that customer's now got two special offers. Now, idempotency is crucial for ensuring that messages or events are not processed multiple times. This can happen when the messages are sent multiple times due to network issues, or when a message is retried after a failure. Without proper handling of idempotency, systems can become unstable, leading to duplicated messages, inconsistent data, etc. Now, there's several techniques for ensuring idempotency, such as using unique IDs in the metadata of that event. In this scenario, I've got an idempotency ID that's generated by the source system.
And then the service can store then processed events in some kind of data store so that that can be checked before processing the event. The only issue here is race conditions really need to be considered, because it might be that event hits the system at the exact same time or within milliseconds. So that second event that's hitting the system gets through the check against its local database because we've not yet stored it in the local database. So we'd have to look into locking or doing sort of multiple checks throughout the process to try and stop that potential duplication. Sometimes it might not even matter, or there might be a kind of natural ID that you've already got. So in the example of the registration event, the service can just simply check against the username or the email address without having to build idempotency IDs, for example. And sometimes it might be fine for a service to just process the event multiple times because downstream in another service, it'll get handled. But overall, in general, it's just important to test for idempotency, ensure that the system behaves as expected when processing duplicated messages. It's not a particularly easy area to test, but it's really important when you cannot rely on atomic transactional code, which is typically what you get with a monolith. Now, outside of the technical issues, one of the big issues of moving to an event-driven architecture is just having poor events in general. And by that, I mean inconsistent naming, duplicate events with different names, events that serve no purpose, events with more than one responsibility, and so on. So the main resolution for that is to have an event catalog. So this is an example of a catalog that you can use. It's worth having a look at. Now, the idea is to document all the events in the system in a single place. Events should be clearly documented with versions, attributes, schemas. And in this catalog, it'll actually show producers and consumers as well. Now, having that catalog will mean that all developers can use it for looking up events, but will mean that they potentially won't create a duplicate event. Also allows aligning events so they're more consistent. Now, the final problem I'd like to touch on is just the 3 pillars of system observability. So logs, metrics, and tracing. Now, these are essential for understanding the flow of events and messages through the system. So without these techniques, it can be really difficult to detect issues such as slow message processing or message duplication. That can lead to data inconsistencies and system failures. There are several common problems in this area, especially in event-driven systems, such as the lack of having a centralized logging and tracing system. We've got all the different systems working together and disparate logs. It can be very difficult to look and find the reason for a problem. The absence of performance metrics can be a big problem, and just the inability to correlate related events through the system. So it's important to use logging, distributed tracing with some kind of correlation ID, implement metrics at key points in the system, and use dashboards and alerts to monitor the performance of the system. Now, there's many tools in this space, some of which I've got on the slide. But finally, it's just important to continually test observability to ensure the system is providing all the necessary information to diagnose issues. You don't want to go to production and add it as an afterthought when you have a live issue at 2 a.m., for example. So in summary, when transitioning from a monolithic architecture to an event-driven architecture, it's important to start small and gradually migrate. Start sending events sooner rather than later. Just make sure you document them as you go along. Now, to allow for safely testing new functionality in production environments, then use dark launches and feature flags. And design for problems that come with asynchronous events. So latency, race conditions, duplication, etc. And make sure that you observe and improve that system over time. It's important to remember that this journey is not a one-time event. It's an ongoing process of learning and improvement. So embrace that power of events. Let your architecture evolve organically over time, and don't be afraid to experiment. Thank you.